I will begin with a word of prayer once I get up here. Heavenly Father, we thank you for this day again. I thank you for this class and these students. Just ask you to just bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I don't seem to have the attendance sheet with me. I'm sorry, guys. I got distracted before class. Something very boring came up, which may affect everything I do. So, oh well. In any event, today I want to talk to you guys about real differential calculus of the plane, which I'll just call real calculus of R2. In particular, we want to think about a function, all right, which is a map from, let's say, R2 to R2, all right? So like, you could say f is equal to f1, f2, right? These are the component functions, all right? The component functions. And so I've pretty much explained to you guys how we take limits of these sorts of things last time, but let me begin with an example just to do a little bit more with limits. Let's look at f of x comma y equal to, let us say, I'll get it eventually here, x over x squared plus y squared minus y over x squared plus y squared, okay? So here's a particular function, and we could, we could calculate this, the limit, as we go to the origin. So that's my question, is the limit as xy goes to 0, 0, you know, what is that equal to? All right? So, so here's the thing. That limit exists if and only if the limit of f1 and f2 separately exist. All right? So we would need both f1 and f2 to have separate existing limits, right? So this is my, f1, and this thing over here would be f2, right? And so for the double, for the limit in the at the origin to exist, we should be able to get the same thing if we remember we did this thing with different path limits in Calc 3. So let's see here. If I look at the limit as t goes to 0 of f of, let's say, t comma 0, all right? What would that be equal to? And what would the limit as t goes to 0 of f of 0 comma t be equal to, right? So let's see, this would be like the horizontal path, and this would be a vertical path, yeah? Through the origin. Yeah? Because like, here's like your typical 0 t, my bad, t0, and here's your typical 0 t, right? And what happens, what do you get? You've got the limit as t goes to 0 of, let's see here, x equals to t and y is equal to 0. So you get what? You get t over t squared, right? Oh man, I'm sorry guys, let me fix this. I didn't mean to quite do this. I meant to do the square root on the bottom to make it more interesting. Sorry about that. Okay. So then I'm looking at the square root of t squared plus 0, right? Which is equal to the limit as t goes to 0 of like t over absolute value of t, right? And I think this one works out the same, right? Actually, not quite. So we get what we get, like minus t over the absolute value of t. All right, so to make this a little bit more interesting, let me actually look at like half paths. All right. Technically, these limits don't even exist, right? Because the absolute value is t from one side and it's minus t from the other. So technically, the left and right limits here don't exist. So like both of the limits I wrote down right now don't even exist. Let's make them exist though, and that's easy enough to do. I'll do like from the right, okay? Just add a little plus here. Then that will sort of give me a little bit more interesting thing to say here. So if I do that, then it's not a path through the origin. It's like these are rays, right? It's a ray. Yeah? Because it's just a ray to the origin. So like this one, right? And this one over here, okay? And as such, how does that work out? Well, we get minus t over, what's the absolute value of a positive quantity? It's just the quantity again, right? So that just gives me a t here. And over here we get what? We get, oh man. Rats, guys. Stink. I'm sorry, guys. I'm so sorry. Look, this is a vector, right? Comma what? Comma what? And over here, I just wrote the second. So this is actually something, comma that, you know? The something is really easy, though. What happens with the other component that I haven't written?
0.
Yeah, there's 0. So like I plug in y equal to 0, that piece is 0. And this piece is 0. Now, and it is literally 0, and we're dividing by something that's only 0 at the limit point. So you know how limits work, right? We consider points close to, but not at. So those are just 0. And I think, yeah, those are 0. And how about the other ones, though? That works out to what? So this works out to 1, 0, and this works out to 0, negative 1, right? So what that tells me is that this limit right here does not exist. If we get two different path limits approaching, the point, and they get a different value for the different paths, then that means that the limit doesn't exist, right? So what this means, let me put it in different notation though. What this means is that the limit as z goes to 0 of z bar over the square root of z bar does not exist. And I'm sorry, guys. This was not actually the example. What I intended to do, I'll just put for example 2. I was trying to do the limit as z goes to z naught of like z bar minus z bar naught divided by z minus z naught. That's actually that's what I was after here. All right, that's the one I wanted to do, and somehow I twisted it in my mind to what I did there. But the one I just wrote, it can be solved in the same sense. Like you can prove that the path limits for that don't agree, okay? So like here, we'll use the complex notation. If we put z equals to say x naught plus it, and I call this thing right here, this business, f of z, right? Well then, f of x naught plus it, what is it? We'll let z naught be x naught plus y naught, okay? I mean, why not? Okay, sorry, standard for comedy low in here. That's good. So that's going to give me, like x minus x naught. My bad. It's going to give me. So what is? So what do I get here? I get I'm sorry. I'll get it eventually here. Let me write this formula out. So we have x minus iy minus parentheses x naught minus iy naught. That's the z bar naught and z bar. And down here I've got x minus x naught plus I times y minus y naught, right? If I write it all out. And I could probably, let me clean this up a bit. Let me put the x naughts next to each other. Let me put the x's and the y's together, yeah? Make the formula better for us. Plus I times y minus y naught. All right, there you go. That's the formula.
So z is x plus it? Yes. Instead of it being x naught plus it.
No, I mean x naught plus it. So this is a particular path. So I want to look at what happens when I put z equal to this. In other words, if I do that, I've got, well, I'm sorry. You guys are not wrong, but you're not right.
Isn't the whole thing?
All right, let me try this again here. All right, so I'm here. So sorry. So that's my formula, and I want to look at. Let me just draw a picture. That'll help. So here's my point: x naught plus I y naught, right? I want to look at a vertical and a horizontal path to that point. Yeah? So like, what you guys want to do first, vertical or horizontal? Vertical. Okay, so that one, I would put z equal to what? X naught, right? Plus what? Plus it, let's say. Then when t equals to t naught, I'm going through y naught, right? Or if you like, I could do like t minus just a second here. So if I do like y naught plus t, there you go. When t equals to 0, we're going through this point right here, right? So if I do that, what is z minus z naught for this path? So it would be what? It'd just be it, right? On the other side of things, on the flip side of things, for the horizontal path, I'd have, a typical point here would be z equals to x naught plus t plus iy naught, right? And so for the horizontal path, I'd have z minus z naught equals to t. See, these are both paths. So if I look at the limit as t goes to 0 of, z bar minus z bar naught over z minus z naught, subject to the, subject to the red path, right? Let me give it a name. Let me call it gamma. Rats. Fine. Let me just go step back here. So what I'm doing is the limit as t goes to 0 of f of gamma of t, right? Where this describes, well, this right here is the formula for gamma of t. But what that actually means, of course, is that z minus z naught is t. And what do we get upstairs? So z bar minus z bar naught is what? So downstairs I just have t, right? How about upstairs? So if this is z, z bar is what? X naught plus t, right? Minus I y naught. And if I subtract z bar naught, which is what? That, right? I take the difference of these two. What happens? You get t, right? So again, we get t. So this limit is 1. But what happens for the blue path? Let me call this guy right here alpha of t, all right? What's the limit as t goes to 0 of f of alpha of t? See, if I plug in that path into the function, I get what? I get z minus z naught is it, right? So I get it down here, and I get minus it upstairs, I believe. Again, the t's cancel, but this time we get a what? We get a minus 1. Right? But the point I just did this for, z naught, is arbitrary, right? It's an arbitrary point. So what does this show? This shows that, if we take the ratio of, well, it shows that this f of z, the limit as z goes to z naught for that function does not exist, right? So like, I'm just telling you is like we can appreciate limits not existing from taking different path limits. And on the one hand, we could adopt like a real notation over there, or we could do a complex notation over here, all right? Okay, so enough about that. This actually has a significance. What this calculation goes to show you soon is that the derivative of the function, if you look at the function if you look at the function, let's say g of z equals to z bar. If we looked at g of z equals to z bar, okay, then g prime of z naught does not exist for any z naught in the complex numbers. Like this calculation we just did proves that. I'm putting the cart before the horse a little bit, but I just wanted to explain the significance. Like, why am I doing this is for later reference, okay? And there's actually a way easier way to see that once we have about 2 more lectures done, okay, guys? All right, so I said that we were going to talk about real calculus in the plane, so let's get to that, yeah? So, definition. How should we define, if we have a function from, let's say, R2 to R2, then how do we define partial f, partial x at the point, let's say, x naught, y naught? How you define that? The way you do it is you say, well, that's really the derivative with respect to t, right? Evaluate that thing at t equals to x naught of what? Of f of what? Well, f of, we're just varying the x, right? So we put the t here, and we freeze out the y. So this is how we do partial differentiation. We freeze one variable, and we vary the other, right? Can you guys tell me how to write that in terms of a difference quotient? How do we write a partial derivative in terms of a difference quotient? So what we do is we would take the limit, right, as h goes to 0 of what? We take f of x naught plus h, comma y naught, minus f of x naught y naught, all divided by t, right? And how would you guys think we define partial f partial y at x naught y naught? Well, like, here's the calculational principle. We do d dt evaluated at t equals y naught after we differentiate, right? And we differentiate what? We differentiate f with x frozen out at x naught, and we let y vary, right? In terms of a limiting process, that's what? The limit as h goes to 0. I'm sorry, I wrote a t down here, but I meant to put h. Yeah? Please forgive me. H, parentheses, parentheses. I did the easy part. You guys tell me what goes in the numerator.
F of x naught y naught plus h minus f of x naught y naught.
F of x naught, comma, y naught plus h minus f of x naught y naught. We have a winner. Very good. Now here's my question to you guys. Did we cover this in Calculus 3? And some of you have had my class, so like that's not a, you know, an unreasonable question. Like I know the answer to it. If others of you had Majeric, I still know the answer to it, pretty sure. And this is not an indictment on anybody else's Calc 3 teaching either, because it's an indictment on mine as well, probably. Notice something about the codomain of the function. Like this is a function from what? From R2 to R2, right? So I just defined the partial derivative of a vector valued map. We typically only talk about partial derivatives of just real valued functions in Calc 3, right? Like, yeah, for the most part. I mean, we do some partial differentiation of vector valued maps for like the surface integral stuff at the end. Like, if you think about the like partial r vector partial u, that's a vector of partial derivatives that would kind of fit into this category. Like the parameterization of a surface is a mapping from R2 to R3, which we partial differentiate, if you think about it. You know what I'm talking about? Like in Calc 3, we had like, here's my UV space, right? You got some parameter domain D, you got your mapping. I usually use an X, some other people use R, and that takes you up to the surface, right? And on that surface, you can calculate partial R, partial V, and partial R, partial U. We did that, and then we took their cross product to find the normal. Right? Those partial derivatives are somewhat akin to the one I just defined, because it's a partial derivative of a vector valued map. So truth is that these guys, truth in advertising here, note that partial f partial x is actually a vector. It's partial f1 partial x, partial f2 partial x, right? And partial f partial y, likewise, is a column vector, which I write as these sneaky hidden row vectors, right? Fine, I'm feeling guilty, so let me write it as an honest to goodness column vector, but I'll use the easier notation. Partial y f1, partial y f2, right? So these are partial derivatives of a map. We take the partial derivative of each component function to find the partial derivative of the map altogether. Okay, guys? It's good? Okay. Hope it's good. So, what is the derivative of a function from R2 to R2, right? Is a natural question you can ask here. And so, for this, I need to make another definition. So, like, basically, the idea is this. The derivative is best linear approximation to the change in f at a point, all right? And the way to make that precise is as follows. So definition, L, which we often denote by the differential at x naught, y naught of f, is a linear function or linear map such that the Frechet quotient limit, Frechet quotient's limit below exists. So here's the limit. We take the limit as h goes to 0 of, here we go, we do f of let me say r, I'll use some vectors here, r vector naught plus, let me not use vectors, I take it back. I'm going to use a p, I'll use a p, that's easier. So p sub naught plus h minus f of p naught, all right, minus, I'm going to use the L because it's easier, L of h. So the change in the map at the, so here this is equal to, this is my point p naught, okay guys? So the change at p naught is given by what? It's given by f of p naught plus h minus f of p naught, right? That's the change in the map at the point p naught. And I want to say that that's well approximated by this linear map L acting on h. And this linear map, we have a name for it, it's called the differential, right? Now, I want to say this is equal to 0, right? But, you know, this is a notion of differentiation, so it's not, it has to involve some sort of like 0 over 0, right? So I'd like to just divide by h, yeah? Kind of like up here, definition of partial derivative, right? But there's a big difference between the h here and the h there. What is the difference now? Like, so up here, h is going into a single component of one of these functions of two variables, right? But down here, I'm adding h to a point. What does h have to be?
It's got to be a vector.
Yeah, it has to be a two-dimensional vector, right? For this to make sense. Can you divide by a two-dimensional vector? Not usually. I mean, yes, you can if it's a complex number, but this definition actually supersedes complex analysis. Like, I'm writing this. Actually, if you look at this, there's nothing two-dimensional about it. What I wrote, right? So what's done is you just put the length of the vector here. You can divide by the length of the vector, and that achieves the purpose here. So if this limit exists for some linear map, then your function, your map rather, is said to be differentiable at p naught. F is real differentiable at p naught with differential d, where was I guess my current notation, d, I'm sorry, let me use my actual notation, d f, I suppose p naught. Let me swap that out for a little d. I usually use little d there. I usually put the point, well, I don't know where the point goes. This is debatable where the point goes, okay guys? I'm not trying to say something pointless, but I kind of did. So I regret nothing. Yeah. This is what we mean by a function of several variables having a derivative. It has a derivative if the differential exists when makes this Frechet quotient go to 0. Notice that in general this would be like an n-variate limit, because if we're talking about a function from like Rn to Rm, the same definition holds, okay? But we're going to talk about functions from R2 to R2 here mostly, yeah? Now, any questions? Like, this is not typically covered in Calculus 3 unless you've got some crazy instructor like me. And I might talk about this for a day, but...
What do you mean by h goes to 0 if it's not a scalar?
If it's not what?
If it's not a scalar.
Well, that's the limit, the multivariate limit to the origin of the vector. It's like the same limit we looked at over there in those two examples. Well, the first example, we looked at the limit to 0. And we showed it didn't exist by two path limits, right? But, I mean, if you want me to be more technical, I can. What that means is that for each epsilon greater than 0, there exists a delta greater than 0 such that 0 less than the norm of h less than delta implies that the norm of the norm of g of h minus, well, I guess just g of h minus L. Well, I use L in a different sense here. Oh well. G naught, there we go, is less than epsilon. That would be what we mean by the limit as h goes to 0 of g of h is equal to g naught.
Wow, that makes so much more sense.
But it is the multivariate limit. I mean, it means all of that. And if you want to, like, it is a genuinely higher dimensional thing, you know? So it's not enough to check all path limits like we saw in those examples. It is the multivariate limit we talk about in Calculus 3. But it means the same thing we mean in Calculus 1, right? It means that if you're arbitrarily close to the input but not equal to the input of the limit point, then the values of the map are close to the limiting value in the sense that the distance from the limiting value g naught to the value of the map g of h is arbitrarily small. It's the same definition as in Calculus 1, it's just now with vector length as opposed to absolute value. All right, so advanced calculus, I take a much deeper look at this, okay? And I basically look at like calculus over normed vector spaces in there, typically. But here we just need a little bit of advanced calculus, just enough to keep us out of trouble. And so let me see how much time I have wasted on my first two unnecessary examples. Ooh, lots of time. My bad. So let me just try to get straight to the point here, which is I need to use the projector, sadly. Because some of this there's some of this I can't really test you on. I want you to know this for context. So, you know, if I spent 2 hours of class time writing it out, it wouldn't be the best use of your time or mine. Because what I want you to understand carefully is the linear algebra of complex numbers in the plane. And, well, there's one theorem we'd like to understand carefully. And I'll write that one out when I get past this little bit here. Well, come on. Make sure I'm not putting up email or something stupid. Let's see here. Let's see, where are we? Okay. Cool. Come on. Whoa. The good news is you missed nothing.
Huh?
You missed nothing. All right. All right. So I got to pick up the pace in here. So you guys, just let me do show and tell for a bit here. So relax. I'll drive. I can't relax when other people are driving. It's just that's how I am. But so we just defined this. This is the partial derivative. I did it in the plane, but here's the definition in Rn. And then like there's a sample calculation right below. Okay, great. A theorem that I just claimed without proof, but here it is. Like this partial derivative is actually the vector of those partial derivatives, right? I mean, I do that in Calc 3, and no one really calls me on it, so it must be true. Now, that is the kind of thing I would actually prove in advanced calc, though, typically. So here's some important examples. And so I'm doing a kind of, we can adopt the complex notation for a mapping on the plane, right? So like, for example, e to the z is really e to the x cosine y, comma, e to the x sine y, right? If we go back into like the a comma b notation versus the a plus ib notation, yeah? So here's the x derivative, here's the y derivative. Check that out. So the x derivative actually is e to the z again. That's kind of funny. And the y derivative, on the other hand, when you work through it, it ends up being I times the complex exponential. And the same thing happens for z squared. Check it out, yo. So this is the real part, that's the imaginary part. Partial differentiate with respect to x, you get 2x. Partial differentiate with respect to x, you get 2y. Lo and behold, 2z. But on the other hand, y derivatives end up giving you, factor out the I here. That's a minus I squared. Tilt your head and squint, you can see it. And so you factor out 2iz. Well, that's an interesting pattern, isn't it? Same thing happened for both of these examples. What's up with that? You know? What's up with that? So here's a theorem that partial derivatives of complex valued maps, and by a partial derivative of a complex valued map, I mean simply we partial differentiate the real part and the imaginary part separate and just string them together like we just talked about, okay? And it satisfies all of the rules that you'd like. Derivative of sum of the derivatives, and you got this product rule. But understand that this is a complex product, okay? This is not something we did in Calculus 3. This is new. That's a complex product. These are complex products. And so my proof down here rests on the component expansions of f and g, so I can see the real part and the imaginary part, and I take the partial derivatives, and the complex product plays together with the ordinary product rule to work out like that. So it's, there it is. I mean, the proof is not especially exciting, but there it is. So check this out, sine of z. So sine of z, if I use the adding angles formula, I can get this component expansion for sine z, sine cosh plus cos sinh. And if I take the cosine z, I get this, right? If I take the x derivative of this, I get that. If I take the x derivative of that, I get that. It seems like the x derivative of sine is equal to cosine. That's kind of neat. On the other hand, if you take sine of z squared, you get this. Anyway, so these are some just sample calculations for this kind of partial differentiation since it's new. All right, I want to make it, I want you to understand it's something new, but also that it's nothing scary, okay? Nothing scary. And things tend to work out like you'd kind of expect they do. Check that out. So like the partial derivative of sine of z squared with respect to x, when I take the x derivative of the components of this thing and work it out, I get 2z cosine of z squared. It's kind of funny, isn't it? Yeah.
Oh, yeah, that's what I was about to ask. Whenever you're doing, when you're taking the partial derivative with respect to x, you'll always get back the partial, like the derivative of the.
Well, that's the question. Is this a quirk of these examples I'm looking at, or is this actually always the case? That's the question, isn't it? Right? Oh, yeah, I guess not. So let's see, here's an example where it doesn't work. So if I look at f of z is the modulus of z squared, right? X squared plus y squared. And if I look at g of z is z squared, then f of g of z is that. And it is not the case that if I, you kind of would expect maybe, well, I don't know what you'd expect, but this is not what happens. Let's see here. Well, I guess you could just stop at f of z. Like if you partial differentiate this with respect to x, you get 2x, right? Which is not twice the absolute value of z, is it? Because twice the absolute value of z might be what you'd expect. Maybe. I don't know. But twice the norm of z would be 2 times the square root of x squared plus y squared. But instead, if I partial differentiate this with respect to x, I just get 2x, right? And if I partial differentiate with respect to y, I just get 2y, which is not I times the x derivative either. So the pattern is apparently spoiled for the modulus squared function, right? Yeah. So we'd like to understand how that happened and why that happened, and I'll give a rather authoritative answer to that next class, all right, if everything goes as I hope today. Well, if I can finish the rest of this class well, let's say that. So I already defined this for you guys, okay? And what follows here is just an explanation of how the Fouché derivative ties together with notions of partial derivatives, okay? So like, basically what I show here is that if the function's differentiable, then that, so I know you guys, some of you have had linear, some of you haven't, but I said that it's a linear map. That means that we can write the formula as matrix multiplication times the input. The matrix of the differential is called the Jacobian matrix. That's the same matrix that you saw in Calc 3 for like coordinate change, all right? In particular, it's a matrix of partial derivatives like this. This is the Jacobian matrix. So for us, for a function from the plane to the plane, it'll be a 2 by 2 matrix. The first column will be the x derivative. The second column will be the y derivative of the map. Simply that. But this is, I've got some n-dimensional formulas here. So you can look at the Jacobian as the concatenation of partial derivatives, or if you like, a stack of gradients. But anyway, this is just calc. This is like that's advanced calc. That's just context, okay, guys? So here's z squared. So the Jacobian for z squared, x derivative, y derivative. So x derivative gives you 2x comma 2y. Y derivative gives you minus 2y comma 2x. That's just going back to that previous example. This one, notice the plus instead of the minus here. Big difference. The big difference is that we don't have the same pattern up there anymore, right? We've got 2x still, but we've got not the minus plus, we've got plus plus there, so different pattern. But notice that the pattern for e to the z is the same as that one. Check it out, right? So like, here's the x derivative for the exponential, and here's the y derivatives for the exponential we were looking at a second ago. When I put them in a column, I get this and that. Notice that this is minus that, and these are equal, just like this one, but not like that one. There's something different about the middle example, like it's not the same pattern. And here's another one. So down here, I have 3z plus z bar, right? So like the real component of it is 4x, and the imaginary component of it is 3y minus y, so 2y. So like in real notation, this is just 4x comma 2y, okay? And so if I take the Jacobian matrix of that, the x derivative, the y derivative, like so. Again, not the same pattern as examples 4.23 and 4.25, right? Different pattern. All right. And these are just for context. Here's like the Jacobian matrix for a path. Here's the Jacobian matrix for a function of function of R6 to R, whatever. You can look at these or not look at these. It's all good. Although here you might have seen this in Calc 3, right? This is Jacobian matrix for polar coordinate change. Take the determinant of this. It gives you the measure for the polar integral. So these things don't matter too much. Now this calculation right here shows you that if you have a function from the reals to the reals and it's Fouché differentiable, then it is in fact real differentiable in the sense of calculus 1. So there's a connection between this new general notion of Fouché differentiation and regular calculus 1 style difference quotient differentiation, all right? And the relation is simply this. The differential of a function of one variable at x acting on h is simply obtained by the derivative of f at x rather, multiplied by h. So for a function from R to R, the Jacobian matrix is just a 1 by 1 matrix. It's a number, and that number is the derivative that we know and love from calculus 1. So this is how the two worlds tie together. Like the Fouché derivative is a natural extension of regular, plain old Math 131. All right. Now, the troublesome stuff I was just talking about at the start of class, the trouble of path limits, that's one problem. There's another problem which is probably somewhat related, which is that of functions which are differentiable but not continuously differentiable. So This is a subtle issue. But it's possible to have a function that you can calculate the derivative at a point. However, that derivative is not continuous. So this will violate some of your intuition. If you read quotes from 19th century mathematicians, they'll say it's the sort of thing that kept them up at night. Like they have nightmares about these sort of things. But they do exist. You know, sort of like adult Swiftie fans. But none of you guys, though. Right, okay. Okay, all right, just checking. Anyway, so down here is this dreadful, so what you're looking at, the red line is the graph of the function, okay? It is constructed such that actually the derivative at 0 exists and it's equal to a half, as it turns out. But the derivative function is graphed in green. So the derivative function, while it exists at 0 and is equal to a half, it is not continuous at 0. In fact, this function, if you zoom in, you can find arbitrarily, on any interval, no matter how small, you can find the function both increasing and decreasing in a neighborhood of 0, because it oscillates wildly at the point. Right? So this is a function which is differentiable, but not continuously differentiable. This will make the nicer theorems go away. So we'd like to assume that our function is continuously differentiable to avoid this pathology. All right. The other thing is the path limit thing. I already talked to you guys about that a bit. Like this function I've graphed. See, it's got the path limit goes to 0 this way, and the path limit goes to 0 that way. In other words, the partial derivatives of this function both exist along the coordinate axes, but this function is not differentiable at the origin because, well, you can't put a tangent line does not a tangent plane does not well approximate the graph of the function at the origin. It tears up and down. It's not actually differentiable in the Frechet sense, even though the partial derivatives both exist. The trouble is that the partial derivatives are not actually continuous at the origin. If you study this, you can look at different path limits and you don't get the same thing for different things. So like the partial derivatives are not continuous at the origin, which is why that function is not differentiable at the origin. You can also have weird stuff like this, which I'm going to skip past. So definition. A function from Rn to Rm is said to be continuously differentiable if the following, if all of the partial derivative mappings exist on an open set containing the point and they're continuous there. So continuous differentiability concerns partial derivatives. You notice that the definition of Frechet differentiable didn't involve partial derivatives directly. All right? But there's a simple, you can prove a theorem. There's a theorem that's not too hard to prove in like advanced that says that if the Frechet derivative exists, then the partial derivatives exist. That's actually fairly easy. Like basically all you do is you take the multivariate limit and you specialize to like path limits along the coordinate axes, and that'll turn the Frechet limit into the kind of limit we have at the top of the board over there, namely the partial derivative limit. That's how you prove partial derivatives exist from the Frechet derivative. You just literally take path limits in the definition of the Frechet limit. The other way is much more difficult. Like how do you take the existence of all the partial derivatives and take those and put those together and build the multivariate derivative, the Frechet derivative? That requires, well, I say it requires, but that's too much. I will tell you this. It suffices to know that the partial derivatives are continuously differentiable at the point. Is that necessary? No. But answering, like, how can you weaken continuous differentiability and still get differentiability for a particular context is a far more technical question that I just leave to experts, okay? So this is a little bit greedy, is my point. Continuous differentiability is a little bit greedy, but it's greed that we endorse, okay? Now, so here is the theorem. If f is continuously differentiable at A, then f is differentiable at A. That's the big theorem here. And so I proved this last year, and I'm tempted to just let you guys look at that, actually, if you're interested, because I'm kind of not doing so well today, proving stuff. So is that okay? If you come to advanced calculus, I'll probably do this proof in about, it takes me about a half hour to do it properly. So, but I can sketch it. Basically what it is you just essentially look at the change in the function you're trying to approximate, and you replace it with a change in the horizontal direction and a change in the vertical direction. And both of those you can approximate using the partial derivative in either the vertical sense or the horizontal sense. You use the mean value theorem, which replaces like the change for a derivative times the change of the input in both ways. And then because you have the continuity of the partial derivatives, you're able to make that limit go to 0 and then prove that the Frechet quotient exists and limits to 0. That's basically the proof. But it's not complex analysis. I don't feel too bad not doing it in here. It's really advanced calculus, truth be told. And you're like, well, if it's not complex analysis, why are you covering it? Because this is the linchpin of like the central theorem that we use for the next couple weeks. It really is advanced calculus. Any complex book buries this theorem in some sort of onerous and somewhat sketchy calculation involving past limits. It's not quite right, in my view. That's why I told you not to read those sections in SAF in the book. Okay, because like what's here is like much closer to truth. But this is n-dimensional. My apologies, I don't have a two-dimensional proof right there. Now, this I'd like actually to understand carefully. Okay, so let me slow down here and try to work through this. Linear algebra of the plane. So we've seen some Jacobian matrices had a pattern that was similar to other ones, right? But not all. Just like we saw some of the derivatives bore out a certain pattern, but not all. And these issues are not unrelated, okay? So let me just get to the theorem here and we'll prove it. So this is the theorem. If you have a mapping from R2 to R2 is a linear transform. Do you guys know what a linear transformation is? If you don't, you can just tell me. Do you know linear transformation? No. Okay, so I mean, it's totally legitimate not to know what a linear transformation is in here. Some of you guys have had 221, so you know. Are you taking 221 right now?
Yes.
Yeah. So you'll find out what a linear transformation is in a couple weeks. There's really not much to it. A linear transformation is a transformation that preserves addition and allows you to pull out scalar multiplication. So to say that t is a linear transformation simply means that like t of x plus y is equal to t of x plus t of y, and that t of a constant times x is equal to a constant times t of x. And so this would be like for all x and y in R2 and c in the reals. So this would define a mapping being a linear transformation on the plane. Now, like some people would say the fundamental theorem of linear algebra is that any linear transformation, well, that a mapping is a linear transformation of column vectors if and only if its formula can be written by matrix multiplication. Okay, so like let me show you that. So let's see here. I'll give you an example. 3, 2, 3, maybe 3. 3. All right, so let me just make one up here. So suppose you've got t of, let's say x1 comma x2 is equal to x1 plus x2 and then 3x1 minus 7x2. There we go. So first of all, by that I mean this column vector. So you can rewrite this as like x1 times a particular column vector plus x2 times a particular column vector. So can you tell me what those vectors would be?
Is it 1 and 3?
Uh-huh.
x1 and then 1 and negative 7.
1 and negative 7. Perfect. Right. So any linear transformation can be written like a linear combination of particular vectors. And then we define matrix multiplication like this. This is equal to also, we make the matrix 1, 3, 1 minus 7, like so, times x1, x2. That right there, this matrix is called the standard matrix of the linear transformation. So this is the so-called, our notation is like this, bracket T. This is the standard matrix. Of T. Welcome to Friday's welcome to Friday's differential equations, by the way.
Really?
Yeah.
What?
Yeah, because we're doing systems in there on Friday. So we're going to be covering matrix stuff in there. That's kind of funny. This often happens.
It's okay.
That's okay.
Oh, it's funny because I'm taking physics 231 right now.
It's too bad I wasn't covering that Monday, right?
No. Well, the things that you're doing in
Too soon?
complex,
Yeah.
like the mission one, it was on my homework. Like a lot of it was like physics.
Ah.
So I knew how to do it.
Oh, the angle stuff. Yeah.
Yeah, I knew how to do it.
I gotcha. So this is the standard matrix. And there's like a formula for it. See, like, what goes on here, the standard matrix of T, if you look at it, what it is you're putting 1, 0 to get the first column, and whatever happens when you put this 0, 1 gives you the second column. All right? And so I sometimes, in linear, we'll call that like T of E1 and T of E2. E1 and E2 are, this is E1, that's E2, okay? Like, we might call it X hat and Y hat in physics or something, or perhaps I hat and J hat in the two-dimensional context. All right, so we good? So that is what we mean by linear transformation in the plane, and that's a standard matrix. Notice that there's no particular pattern here. Like, if you think about the way that the first column and the second column are related, the answer is they're not. For a linear transformation in the plane, just an arbitrary one, a real one, there doesn't have to be any relation between these two. Just like the Jacobian matrix. See, the Jacobian matrix for a function of two variables, it just has the form partial f, partial x, partial f, partial y. See, and for an arbitrary real differentiable function, there doesn't have to be any kind of relation between these two, right? But apparently there was some kind of relation between these two for some of the examples we looked at, right? And that's a mystery we're going to answer next class. But let's try to appreciate this theorem today. So what does it mean for T to be complex linear? I have a definition that I skipped over because I'm forging ahead here. So to say that a function's complex linear means that you can write the formula by multiplication. Oh, thanks, Shane. So definition, T from R2 to R2 is complex linear if T is equal to like multiplication by alpha. And so like L of alpha, if we have that act on, say, Z, that's equal to alpha Z. So this is just left multiplication by alpha, which is a complex number, okay? So this is definition. Like a function is said to be complex linear on the plane if its formula can be constructed as multiplication by a complex number. This is what I mean by complex linear, okay? Like the definition's right here, but so. All right, so I think we have all of the necessary definitions. Now we can try to prove the theorem. So the theorem is that these four things are equivalent. T is complex linear, that you can pull out complex scalars from the input, right? You can pull out complex numbers from the input, or that the standard matrix of T has this special form, right? Or that